And then they also have like a house up there, a hotel or something.
Hello, everybody. All right, we're nearing the home stretch on contrasts. So now would be a good time to finish up the chapter 9 and move on to the Kirk paper. The Kirk paper basically covers the last topic that we'll talk about with respect to contrast, which is multiple comparisons. And that's actually sort of a broader topic. It applies to a lot of different things besides contrast, which is something that I'll emphasize some on Wednesday. The Kirk paper in particular goes through, there are like dozens and dozens and dozens of different ways of dealing with multiple comparisons in the context of categorical variables. That's what the Kirk paper covers. So in that sense, it's a good reference. Yes?
So we should read the Kirk paper before next take-home event too?
Yeah.
Okay.
Yeah. So everything at the until the end of this week is going to be covered on digital, including Wednesday's class.
And we're covering the part 2 from our drill today in class, the homework question that Oliver said.
Yeah, so we'll talk about interactions when you have multiple categorical variables. And
With different amounts of each category.
yeah, or with different events in each category. Are you asking?
With different amounts, it's like A has, factor A has 2 categories and factor B has 3.
Oh, yeah. Yeah, we'll cover that case.
Today.
And if when I get to that section, it's still a little bit unclear how to do that homework problem, I might put together something in email to distribute to all of y'all, and I'll probably give it a little bit more time on Wednesday. So let me know. So today, we're still dealing with these 2 cases of the 3 cases that I laid out at the start of the unit. And in fact, we're still talking about additive and interactive models when you're dealing with one of these 2 cases. So you're going to find today that I'm going to go through a lot of similar content just applied to different areas. And one thing I want to say about both this class and a lot of other lectures from here on out is that most of the time we'll be dealing with some familiar concepts and some concepts that are new. I'm not going to go through every single case that you could analyze with each of these different methods. I'll go through a couple, and then I'm hoping that because you're seeing some familiar concepts, you'll be able to generalize to cases that you're interested in on your own. So today I will go through a couple of major cases that you'll likely encounter when you're doing data analysis. But as I said, research is really varied, and the nice thing about learning the conceptual underpinnings of these different models is the ability to generalize. So I'm hoping you can do that on your own. So we're still going with this hypothetical example of people who are assigned different kinds of beverages, alcohol versus placebo versus nothing. Last lecture, I introduced the idea that maybe differences in startle or anxiety that are less than 20 are not clinically relevant. So we're still going with that. The outcome is still in the startle response. What's going to be different in the case that I'll talk about next is the hypothesis. So I've talked in the past about this idea that maybe the physiological effect of alcohol and the effect of expecting to drink alcohol have effects that add up together. So if you drink alcohol, part of the reduction in anxiety might be due to the physiological effect, and part of it might be due to the effect of expectations. This research scenario is slightly different from others that we've looked at in that the purpose of the research scenario is to estimate some quantities. So there's not like a hypothesis in the way that, I've said, like maybe alcohol has the largest effect and placebo has a moderate effect and drinking nothing has no effect. Instead, we're just interested in estimating two quantities. The first is the pure physiological effect of alcohol, so the effect of alcohol independent of expectancy effects. And the second is the pure effect of expectations independent of the effect of alcohol. So if you had to guess, if you wanted to estimate the pure effect of expectations and the pure effect, physiological effect of alcohol, what kind of set of contrasts do you think we might be working with in this scenario? So here's the hypothesis. Yeah.
So for the first one, you could do negative or positive 0.5 for alcohol, and then the negative positive for placebo, depending on. So maybe positive 0.5 for alcohol, negative 0.5 for placebo, and 0 for, 0 for nothing.
So positive 0.5 for alcohol, negative 0.5 for placebo, and what was nothing?
0.
0. Yeah, so it looks like we definitely want to compare alcohol to placebo because that allows us to sort of subtract out the effects of expectations. Great. What about C2?
Would be the same, except instead of for, it would be 0.5 for alcohol, 0 for placebo, negative 0.5 for. Or sorry, the placebo would be 0.5 and alcohol would be 0.
Is this what you're thinking?
Yeah.
Well, so there's, this isn't quite right because it looks like these might be correlated with each other.
Oh.
Actually, this is a case where planned orthogonal contrasts don't quite get us what we want, right? Because it seems like to estimate the pure physiological impact of alcohol, you want to compare alcohol to placebo. And to get the pure effect of expectations, you want to compare nothing with placebo. And there's a type of contrast that allows us to choose one particular group and compare all the other groups to that one particular group. Anybody have an idea of what that is? Tony code. Yeah. So.
Is there a specific name for that though? I'm just like remembering from drill. There's a specific name of that type when you're comparing like ones sequentially.
Oh, so that's a Helmholtz contrast. What a Helmholtz contrast does is it allows you to compare one group to the average of the others, the next group to the average of the others. So that's not quite what we're looking for either. We want to make two, these are called pairwise comparisons, often called pairwise comparisons. We want to make comparisons between one group to another, and another group to another. And so the difference from a planned orthogonal contrast is that these kinds of contrasts are correlated. I've demonstrated how this works once in lecture, and I have another demonstration here. We'll review it again. But if you see this pattern where your hypotheses, or these aren't even hypotheses, this is about more about estimation. But the thing that you're interested in is like comparison between one group and another group and another. Chances are you're going to be dealing with dummy codes. So these dummy codes are also different from the ones that we've worked with in that I've made placebo the reference group instead of nothing. But let's just illustrate. You can choose whatever is your reference group. Doesn't really matter. When I introduced dummy codes before, I talked about this problem that you often encounter when you're dealing with pairwise comparisons, in that often you're interested in two quantities, and it's like your hypothesis is split across two quantities. That's true here, but it seems like each quantity that you're estimating deals with a different scientific hypothesis. So it's like the comparison of placebo to alcohol deals with whatever theories you might bring to bear about the physiological impact of alcohol, right? Whereas the effect of expectations sort of seems like it deals with a different set of theories. So this is a case, and there are other cases like this, where even though you're interested in two quantities, it seems like if it is the case that, say, C1 is 0, that probably bears on theories about the physiological impact of alcohol, but not about the expectations that people bring in. Likewise, if C2 happens to be 0, that'll bear on theories about expectations, but not about the physiological impact of alcohol. Both of these can be true, both of these can be false, but the truth or falsehood of one versus the other sort of get at independent assessment questions. So this is sort of case where you have like multiple theories and different theories bear on different quantities that you're estimating. That's a sort of scenario where you don't have to worry about the fact that your hypothesis is split across multiple quantities, and where you probably don't have to correct multiple comparisons, which we'll talk about in this second. So this is not only a good use of dummy coding, but it's also a case where you can probably just look at dummy codes without doing anything special extra. People clear about that? Yeah.
So probably new figure this out in drills or class, but with dummy coding, I guess I'm just wondering, how does R know that you're only looking at the reference group compared to the group in the contrast of one?
So the way R knows is it's whatever you set to be 0 when you're creating your mechanical variables. So that's the reference group. And if you want to know how that works, like under the hood, again, I have a couple of graphs that maybe will help clarify this. But the overall answer is whatever you set to be 0 in all the contrasts, that's going to be the reference group. Yeah.
I think, like, going off of what Josh asked, I guess, how does it know not to average placebo and nothing and the first one and alcohol and placebo?
Yeah, so I think you're asking how does that work under the hood? And it has to do with this idea of controlling for the other contrast. Hold that question. I have a graph that maybe will clarify this, and then I'll ask again to see if it's clear.
Okay, and also, like, just my other question that would apply to Twitter is how to interpret that in the output.
Yeah, so we'll go through some output in detail, but the overall answer, and we'll get more specific in just a bit, is that each of these is a mean difference between the thing that's coded 1 and the reference group. Is that clear? Okay. So first we'll review, like, what does an additive model look like when you're using dummy codes? And the answer is it'll look very similar to an additive model when you're using POCs. Or it'll also look very similar to, well, basically a model that you might have used with any other variable, any other additive model. The main difference is that with dummy codes, you're looking at a series of mean differences between a group of interest and a reference group. So let's go through this and see what it looks like. When I talked about categorical variables, I go through this process of taking the text labels and then replacing those with the numbers that we've chosen. So let's do that. So here's what we're starting with. And this is actually the exact same data that I used for my lecture on Wednesday. So if you want to compare what does it look like if you're using dummy codes versus POCs, you can compare these two analyses to see. So, okay, the first step is I'm going to color code each of the groups. My color coding is a little bit different because I switched up the colors to try to make things a little bit more visually apparent. For this first graph, all I've done is I've replaced the previous x-axis with the values for C1. So, of course, notice how both placebo and nothing are sort of mixed together at this point. There's no way to distinguish the two except by the color that I have. So this looks very similar to the process that we went through for plane orthogonal contrast, for example. What's different is that C1 and C2 are correlated, whereas by design, when you're using plane orthogonal contrasts, your contrasts are all uncorrelated with each other. So dummy codes are correlated, and that's actually integral to how you end up interpreting them. If they were not correlated, then indeed, you'd be looking at for C1 alcohol versus the average of placebo versus control. But by allowing them to correlate, you don't actually, when you end up doing the analysis, you don't really do the analysis on the raw data. Instead, you do an analysis sort of on adjusted data. You have to adjust the data points for the other independent variables in the analysis. What ends up happening is you subtract out the effect of C2 before you look at what's happening with C1. So this is what that looks like visually. What ends up happening is that the points in black, the nothing points. So that's that category that's coded 0, but it's not the reference group. Those all get adjusted down. And in fact, the new mean of those points will be the same as the mean of the points for the placebo group. That's one way of understanding what it means to adjust or control for another variable. You sort of subtract out the effects of whatever other variables are in the model before you analyze, before you go through the process of finding that best fitting parameter estimate, that best fitting line for the thing that you're interested in. So this adjustment process, which only happens because C1 and C2 are correlated with each other, is why C1 ends up taking on that interpretation of the mean difference between placebo and alcohol. You adjust the points that are not in the reference group down so that they take on it's called a conditional mean. They take on a new mean, an adjusted mean that's the same as the points in the placebo group. So is this clarifying your your questions.
Yeah, so mean becomes the same as the reference group mean,
Yes.
but standard error increases.
Standard error decreases, but yes, so you get extra precision. You can see like the scatter in the black group is about the same as the scatter as the orange group. This is sort of giving you a cue visually that they're both contributing to your estimate of the error. Is that a little bit clearer? So you adjust for the other variables in the model. It's that adjustment process that allows you to interpret these coefficients as mean differences. So I'm going to take away the color coding for a second because that's what's happening with C1 and C2. But we have an extra variable that we want to think about, that we want to add to the model. So for that, here's another place where I changed the color coding. So red, the red points are the points with my covariate. So the red points are low in the covariate, green points are high. And if I wanted to add an extra variable, so like baseline startle, the level of anxiety, the trait level of anxiety that you have, I can both draw a prediction line for C1 at the mean of baseline startle, and I can draw prediction lines at a low level of baseline startle and a high level of baseline startle. So this is the same process that we followed when we were looking at planned orthogonal contrast or adding on in any other variable into the model. In order to sort of display the extra information, you can color code according to whatever other variable you're interested in, and you can draw extra prediction lines, each of which represents the effect of C1 at a particular level of whatever other variable that you have in the model. Is this clear?
Patrick, real quick.
Yeah.
So, just trying to recap what you just said there. So, we're looking at like a specific amount of startle, the difference between placebo and alcohol group. Is that correct?
Yes. So this is the prediction line for the difference between alcohol and placebo at a low level of baseline startle, at the mean of the baseline startle, and then at a high level of baseline startle.
So here, not it doesn't seem to be much of a difference between those two groups.
Yeah, so there's not much of a difference between placebo and alcohol, correct? And you can see that because the slope of the line is essentially flat. Yeah, was there a
Is
question?
that gray bluish line just an average between all of them?
Yes.
And so this is still an additive model, you've just added a covariant.
Yeah, and how do you know that it's an additive model?
Because it's all the slopes are
Because all the slopes are the same. Perfect. So here's the results of fitting this model. If you ask R to tell you the results. So one interesting thing about using dummy codes, often when you're using, say, plane orthogonal contrasts, it's handy to use centered contrasts. So contrasts where the average value across all the numbers that you're using is 0. But notice the average value across nothing, placebo, and alcohol is a third, as is the average value across C2. So for both C1 and C2, if you take the average of of those three numbers, you'll get a number that's not zero. The implication of this is that whereas whenever we were looking at planned orthogonal contrasts, we found that that intercept was like the grand average, the grand mean. In this case, the intercept is the average value in the reference group, the thing that's coded 0. So whenever you're thinking about the intercept, it's the predicted value at 0 in all of your predictors. While for C1 and C2, 0 is the placebo group. And I've also centered our covariate. So the center of the placebo group will be somewhere around here in the center of all these means, actually where the yellow line crosses the dotted line. Okay. So I gave you the intercept because this was a little bit different from many other models that we've looked at. What about C1? C1 ought to be something that you can figure out how it's represented on this graph.
Just the slope of any of those lines?
Yeah, I have 3 lines, they all have the same slope. The slope of all those lines will be the coefficient for C1, because that's what I plotted on the x-axis, is C1. And it's very close to 0 in this case. At this point, I mentioned how I'm just dealing with this hypothetical example where difference is smaller than, say, 20, might be considered unimportant for clinical purposes. So I can use that information to do an equivalence test. An equivalence test is where you're testing whether a coefficient fits within an upper bound and a lower bound. You do a one sample t-test against the upper bound, and one sample t-test against the lower bound, and if both of those are significant, you can say that your parameter estimate is smaller than the threshold that you care about, this clinical threshold, for example. So this is just showing you those 2 tests. I'm using linear hypothesis test, LHT, because they're one sample t-tests, I'm permitted to divide each of these p-values by 2. Even though this is less than 0.05, or that divided by 2 is less than 0.05, this is not, so we cannot say that this value is smaller than that clinical threshold that we care about. Yeah.
I'm processing more slowly today for some reason, but the estimate for C1 you said was the slope of the lines, which should be close to 0, but -7 doesn't really seem close to 0.
It's just based on the scaling. So notice we have some points that are all the way up here at 300, some that are all the way down at -100. That's showing that there's a lot of variability. I mean, it's all just based on whatever it is that you're measuring. These are microvolts. I tried to make the standard deviations about what you'd see in one of these sterile studies. So
what we're seeing is that there's not a meaningful mean difference between alcohol and the average of those 2 groups.
So to be, yes, let me correct just a little bit. It's the difference between alcohol and placebo, so it's always the reference group, is not different from zero, but it's not small enough that we can say that it's below this clinical threshold that we're doing. Or it's not significantly different, significantly smaller than that clinical threshold. C2 is not something that we can pick out of this graph because I've eliminated the color coding that tells us what is placebo and what is not. So it's not something that we can see on this graph, although I can create a different graph where C2 becomes a little bit more apparent. So let's do that. Before I get there, baseline startle is represented by the vertical distance between these lines. I've gone out 100 below the mean and baseline startle, 100 above. I could have gone out one on either side, and that vertical distance would have been 0.6. I just went out a little bit higher, a little bit more, so that you could actually see the differences between the lines. Yeah.
Sorry, just to make sure this is clear for me. Is this saying a 1 unit increase in baseline startle increases your outcome startle by whatever amount?
5.6. Yeah,
Okay, gotcha.
that's exactly right. Okay, so let's look at that other graph. This is where we started with, where you have 3 groups, and I've added in the color coding to allow us to differentiate these different points. This graph looks very similar to the graph of C1, except now alcohol and placebo are both over here at 0, and nothing is over here at 1. But just as was the case with C1, when we think about the effect of C2, we have to take into account the fact that our contrasts are correlated with each other. We have to adjust the points for the effect of C1. So what I'm going to do again is just subtract out that effect of C1. So I'm taking each point and subtracting out the C1 variable times the coefficient for C1. It's literally what we're doing. And notice once again, the points in the alcohol group, the thing that is not the reference group, that adjusted up just a bit. And in this case, the adjustment is smaller because, as we saw, the coefficient for C1 is quite small. It's about 7, which is small for this variable of startle that we were talking about. The adjustment, when we were looking at the graph for C1, the adjustment was larger when we adjusted for C2 because the coefficient for C2 is larger. That's what we're seeing here. So now I'm taking away the color coding, and we can find that best fitting line just as we have for all the other variations of the general linear model. You know, twist around the line, find the one that minimizes the sum of the squared errors. And if I want to incorporate information about my covariate, which is based on startle, I can just draw these multiple lines at different levels of baseline startle. Notice how similar this graph looks to the one that we just that we just finished with. The only real difference is that these slopes are positive and they're larger. Well, both of these are dummy codes, so it makes sense that we apply a different dummy code. It's going to have a similar format as other dummy codes. So This is the results of fitting that, or these are just the same results that we looked at before. And now we can see C2 on this graph, which is just the slope of each of these lines. I plotted C2 on the x-axis. It's going to be the slope. Or another way of thinking about it is that it's the mean difference between my reference group, placebo, and the nothing.
Earlier when you were saying you were adjusting for the means, you're saying you're making, sorry, I didn't understand this, but you're making the mean of both alcohol and placebo the same.
Yes.
Okay.
Yeah, one way to think about what you're doing when you make that adjustment is that you're subtracting out the mean difference between placebo and alcohol. So C1. And in the process of subtracting that out, what's left is the mean difference between placebo and alcohol.
So is the process of subtracting out the other group something that's automatic when you do the dummy coding, or is that something you have to do with some additional stuff?
It's automatic. It's automatic when you fit your model. This is one way of thinking about what it means to control for something. Is you're subtracting out its effect before looking at the effect of something that you care about.
So your output for C2 is taking into account that it's controlling for C1.
Yes. Yeah, and the way, exactly. And the way that LM knows to do that is that you just add that plus, C1 plus C2. Just to reemphasize this, we worked with a bunch of these models with multiple variables. This is one way of understanding what those models are doing. So there's nothing like inherently different about dummy codes that makes the process of controlling for somehow different. This is that same process. It's just a different way of understanding it. Okay. There's one last graph that we went through when I introduced these additive models. And that's a graph that has my covariate on the x-axis instead of C1 or C2. So I'm just showing you that I'm centering baseline startle, but notice the points are all the same. I just changed the axis. And now I'm adding in color coding, that same color coding that I started us with, where nothing is black, placebo is orange, and alcohol is blue. And another way of understanding this model is that it allows me to draw multiple prediction lines, one for each group. One for nothing, one for placebo, and one for alcohol. This is actually the exact same graph that I showed you when we went through planned orthogonal contrasts. I'm working with the same data set. I'm just analyzing it using dummy codes instead of using planned orthogonal contrasts. So notice I can still get to the same graph using dummy codes. It's the same data, just represented in a slightly different way. So this the intercept is slightly different from when we worked with planned orthogonal contrasts. In plane orthogonal contrast, remember the intercept referred to the average of the three groups because I centered all of the contrasts. But here, actually, should adjust where this arrow is pointing, but the intercept is the mean of the placebo group. And I have a line that represents the placebo group. So where this orange line meets the dotted line, that is the intercept from our model. The reason this is true, once again, is that the intercept is always the predicted value at 0 on all of my predictors, while 0 on C1 is the placebo group, 0 on C2 is the placebo group. Okay. What about C1? Where do you think that might be represented on this graph?
That's the slope of the alcohol line, right?
So the slope of these lines is going to be the effect of whatever's on the x-axis. And I have baseline startle on the x-axis. And notice, of course, how the slope of all three lines is the same. So it's something else about.
It's the difference between both lines.
It's the difference between.
Placebo and alcohol. Or is it?
Yes, exactly. So it's the vertical distance that you have to travel when you go from the placebo line to the alcohol line. Notice how the effect of C1 is quite small. It's minus 0.7. And there's not much vertical distance between these two lines. Each of these points represents the predicted value in the placebo group. Each of these points on the blue line represents a predicted value on the alcohol group. If I want to know the difference between those predicted values, I find that vertical distance. What about C2?
Vertical distance between nothing and placebo.
Absolutely. So remember, each of these contrasts represents a mean difference between the reference group, the reverse coded one. That 51.97 represents the predicted mean difference between the placebo group, which is the reference group, and the nothing. It's this vertical difference right here. And I've already talked about the baseline startle effect. It's the slope of any one of these three lines. If they're going to plot it on the x-axis. Okay, that's the additive model. Probably have some intuitions about what changes when I go to an interactive model, because I've shown these kinds of graphs whenever we've looked at interactive models. Just to be clear about what hypothesis this is testing, we're going to assume that the hypothesis is that the physiological effects of alcohol, so that difference between alcohol and placebo, is larger for people who are really anxious or are high on trait anxiety. Seems intuitive. So if you're really anxious at a baseline, you get more relief from drinking alcohol. So these are the contrasts. And in order to test and an interaction between something and something else, you literally create mechanical variables that are the product of the two things that you want to interact. It's the same with dummy codes as it was with playing orthogonal contrast, as it is with anything else that we work with in the general linear model. So I could literally create those mechanical variables in my data frame. But I don't have to. I can use this handy syntax that goes with LR. That's it. So this is one of the graphs that we work with, the one that shows C1 on the x-axis. Let's see what happens if I go from an additive model to an interactive model. So by going to an interactive model, one way of understanding what you're doing conceptually is that you're allowing these three lines that I plotted to have different slopes. I'm allowing the effect of C1, the difference between, say, placebo and alcohol, to vary by baseline startle, or alternatively, I'm allowing the effect of baseline startle to vary by the difference between placebo and alcohol. So if I look at the output from this new model, notice I have those two new parameters. The parameters for the interaction between C1 and baseline startle and C2 and baseline startle. So let's think about that first one, that first parameter. Where do you think that first parameter is represented on this graph?
Would it be 1/100th of the different slopes between yellow and the red of the rainbow?
Absolutely. Take two of those lines, that parameter is proportionate to the difference in slopes between those two lines. It's 1/100th of it. This parameter tells you how much the slope of one of these lines will change if you increase the unit.
So if you were interpreting that output, what would you say?
I'd say that the difference between the predicted difference between the placebo condition and the alcohol condition increases by 0.56 microvolts for every unit increase in baseline startle.
For every 1 unit increase in resistance?
So one way of thinking about that is that the the physiological effect of alcohol is predicted to get stronger for every unit increase in baseline startle in treat anxiety.
Is it going proportionately the opposite direction once you go below the baseline scale?
Yeah. Okay. So what we have here is in our data, the difference between placebo and alcohol is negative if you're really low in anxiety. I don't know if that makes sense in the context of this hypothetical scientific problem, but that's what our data shows. And it gets positive for people high in baseline anxiety.
Proportionally so, right?
Yes,
Same degree.
exactly. So the difference between placebo, or the predicted difference in placebo and alcohol, changes by the same amount no matter where you are in baseline startle. Of course, there are ways to relax that constraint, but that would make the model more complicated. So the second interaction term, we don't see, it isn't visually apparent on this graph, just like the effect of C2 is not visually apparent on this graph. In order to see what that interaction term, we'd have to go back to our second graph, where we have C2 on the x-axis. And if we go from an additive to an interactive model, one way of understanding what's happening is that the slopes of the lines differ in the interactive model, or allowing the slopes to be different. So that second coefficient, the coefficient for that second interaction term, represents that difference in slopes. So one way of understanding what's happening here is that if you increase the unit in baseline startle, the predicted difference between placebo and nothing should increase by about 0.21 points. 0.21 microns. So just to emphasize again, even though you can think about these terms as representing mean differences, these are exactly the same concepts that we've always applied to interactions. There's really no difference. That's a nice feature of the general linear model. It gives you a set of tools that apply in tons and tons and tons of cases. And they apply in essentially the same way. So that was true when we were working with, say, two quantitative variables. It's also true when we're working with dummy codes and another group. All right, this is that last graph that I showed you, that last way of understanding these three groups. So this is what happens as we go from the additive to the interactive model. And once again, this graph is exactly the same one as I showed you when we analyzed these data using planar orthogonal contrasts. So we can both planar orthogonal contrasts and dummy codes allow you to construct this graph. They both provide the same predictions for your data. They are just different ways of representing those predictions, different ways of constructing those predictions. Okay. So given your understanding of dummy coding and how it gives you comparisons between a reference group and some other group, where do you think C1 is represented on this graph?
Difference in slopes between alcohol and placebo.
Absolutely. that's yet another way of understanding what this coefficient is. It's the difference in slopes between that orange line and the blue line. The prediction line for this placebo group, and the prediction line for the alcohol group.
To clarify, that's not what C1 represents, but it's the interaction between C1 and baseline startle.
Yeah, I said C1, I misspoke. The interaction between baseline startle and C1 is that difference in slopes. Thank you. And what about the interaction between C2 and baseline startle? What do you think that's represented?
Would it be the difference in slopes between the nothing black line and then the orange placebo line?
Perfect. So placebo is still the reference group. The thing that has a 1 is the nothing group. That interaction term, that coefficient for the interaction, is the difference in slopes between the placebo group, or within the placebo group and the nothing group. Perfect. So that's one case. We're still working with a quantitative variable. Now I want to go through a case where our other variable is dichotomous instead of quantitative. I don't know if we'll have time to go through everything that I have planned for this case. If so, it'll spill over to Wednesday. But I think we'll have enough time to go through what you'll need for the homework. We'll evaluate once we reach time. So the change that I made to this data set is that instead of baseline startle being our covariate that's measured before the manipulation of the average condition, I've now upped the N a bit, and so we have males and females, each of whom is exposed to one of these 3 conditions. Still assuming that we have this criterion for what's considered small, in case that's relevant. We still have the same outcome. I thought I'll have to correct this on the slides. I'm also going with a similar basic hypothesis. So I'm estimating the physiological effect of alcohol and the physiological effect of expectations. But now I expect that the physiological effect of alcohol will be larger for women than for men. It has to do with body fat. I don't know the science behind it. But I know that this is generally true in these kinds of studies. So I'll correct this on the slides. The hypothesis is similar to what we were just looking at. So in order to represent dichotomous variables, generally what we've done is we've just given 2 numbers to the different groups. As long as the numbers are not the same, that will allow you to estimate the effect of that dichotomous variable. But it's often convenient to work with numbers like -0.5 and +0.5. So yeah, is there a question?
No, I'm positive.
What do you have going on with the B and the S?
Yeah, so to differentiate, so we have multiple C1s now. I've called contrast 1 for the beverage condition, B_C1, the new beverage. And we have 1 contrast for sex. That's what the S is. Okay. So one way of understanding this new design is that I have 6 different groups. 3 of them for males. So this represents, for example, the effects alcohol on baseline startle for males. And I have the same sets of groups, but for females. So I'm starting with 2 similar graphs, each of which have text labels. I haven't yet replaced these text labels with filters. So this looks fairly similar to where we started with other kinds of categorical variables. You start with text labels, and you can just show points that belong with each text label. So I'm going to follow a similar process to try to represent this kind of design. So I'm color coding each of these points with the same color set I've used before. And I'm going to replace that x-axis, which is not friendly to the generic linear model, with C1, which is more friendly. And this is what that looks like. Very similar to what I just showed you, because placebo and nothing have the same number. I'm sort of smushing together the points that belong in each of those groups at 0. And then I'm putting the points for the alcohol group up here at 1. And just as before, if I'm thinking about the effects of C1, I need to adjust for the effects of C2. So that's one special feature of dummy coding, is that dummy codes are correlated with each other. That means in order to find the parameter estimate for one of your dummy codes, you need to adjust for the effects of the other dummy code. And literally, this is a process of subtraction. You subtract out C2 times its coefficient, that gives you the adjusted points. What ends up happening visually is that the black points move down to meet the orange points. This is exactly the same process that I showed you before. I'm just doing that twice because I have 2 separate tables, one for males and females. If I then replace my male and female labels with like -1/2 and +1/2, well, that looks like baseline startletip, right? That's just some variable with numbers. So I can, just as I found separate prediction lines for mean baseline startle, mean +1, mean -1, well, in exactly the same way, I can plot, say, 2 prediction lines. One for males and one for females. Notice how each of the prediction line has the same slope. The lines are just slightly offset from each other. You can't see it here, but basically the intercepts are different. Same slopes, different intercepts. So I'm treating this extra variable just like we've treated any other covariate in the general linear model. You have to adjust for it, and then you can find, once you've adjusted for it, you can plot separate prediction lines at different values for that covariate. And in a similar way, if I fit an interactive model, sort of what I'm doing with that interactive model is I'm allowing these slopes to be different. So before, in the previous slide, the slopes were forced to be the same, but part of what an interactive model does is it allows those slopes to be different. I hope you're seeing how very similar this case is, case that we just went through, or any of the other cases that we've gone through. In order to analyze this design, in fact, you go through like exactly the same process in R. So you have, we're working with dummy codes again. You have C1 and C2. You create product terms of C1 times your covariate, C2 times your covariate. It's just that in this case, my covariate is sex, another contrast that I created. So it might seem like these cases, have some differences, but the process that you go through in order to fit a model that corresponds to this design is exactly the same. So if you had to guess, based on the discussion of how we handled this design with baseline startle, what do you think that coefficient, or how do you think that coefficient is represented on these graphs?
Difference in slopes.
It's the difference in slopes.
Males and females, or nothing compared, or placebo compared to alcohol.
Exactly. That coefficient represents how males, how the difference between placebo and alcohol differs for males versus females.
So this is the same thing we did before, but we're just using a dichotomous.
It's exactly the same.
Direction.
Yes, absolutely. It's exactly the same. In attack, we've also looked at designs that are very similar like this last semester. So we looked at two dichotomous variables. Well, now I've added an extra group to one of my variables that has to be represented as two coefficients. But I don't know, it's fairly similar in structure. So if you had to guess based on that interpretation, so it's the difference between alcohol and placebo for males versus females. Remember when we've looked at dichotomous variables, we can think about them in terms of means. So this right here is the mean for each group in my design. Which means do you think are involved in this interaction term?
All of the means except for the nothing, for both techniques.
Yes, exactly. So everything except for nothing, and you want to take a stab at what the specific mean difference would be. So once you have those four means, how do you use them to create this this 42?
Oh, it's just like, would it be like how you create a slip? So you could do like male alcohol minus placebo or female alcohol minus placebo?
Exactly. So these are the four means. One way of understanding this 42 is that it's the, for males, the difference between alcohol minus placebo minus females, the difference between alcohol and placebo. So it's a difference of mean differences. This principle will be true for plane orthogonal contrast too, right? This plane orthogonal contrast you can also understand as transformations of means. Well, if you want to know how that transformation of means is different for, say, males versus females, or a control group versus an intervention group or whatever, you fit this kind of model. You allow those contrasts to interact with whatever your dichotomous variable happens to be. Okay. So now I'm showing you slightly different graph, one where this is the C2 dummy code. So I'm looking at the difference between placebo and nothing rather than placebo versus alcohol. And just as when we were thinking about C1, in order to figure out what the coefficient for C2 is going to be, we have to adjust for C1. So we have to subtract out the effect of C1. If we do that, literally what happens is that the points in blue, the alcohol points, get brought up so that their mean is the same as the mean of the placebo group. It's one way of understanding statistical control. If I want to have some way of understanding the effects of sex, participant sex, one way I can do that is I can plot two different prediction lines, one for males and one for females. They'll have the same slope, but the intercept will be offset. If I want to allow participant sex to interact with C2, one way of understanding that is that I'm allowing the slopes of these two lines to be different. Very similar process, the same process that we just followed, the same process that we followed when we were looking at baseline startle instead of participant sex. So if you had to guess, how would this interaction term, the coefficient for C2 by participant sex, be represented on this graph? It's the difference in slopes. Yeah, absolutely. And which means do you think would be involved in the computation of that, the coefficient for that interaction?
Alcohol, right?
Yeah, so alcohol is the thing that's being left out. It's going to be everything except for alcohol. And specifically, if you wanted to compute that interaction term from these means, what would you do? Yes, the difference of differences, and which differences? Yeah, so you take the difference between placebo and nothing for males and subtract it from the difference between placebo and nothing for females. Or the reverse, you just slap a negative on it. So
Does it matter which one comes first?
it'll just affect whether the coefficient is negative or positive. Technically, it goes in this direction in this specific case. You just want to understand where it comes from. So I don't want to keep you too long, but I do want to get to this point. One way of understanding what we're doing is that we have 6 different groups in this design, right? We have 3 groups for males, nothing, placebo, and alcohol, and 3 groups for females. So what I've done for these 2 contrasts is that I just duplicated these numbers for males or females because, you know, they are each treated the same when I'm thinking about the pure effect of the comparison between placebo and alcohol. And likewise, when I'm looking at the pure effect of placebo versus nothing. I have yet another contrast in this design that compares males to females. I put -1 and +1 here because it's a little bit easier to understand. It'd be very similar if you had -0.5 and +0.5. So one way of thinking about what we're doing is that I've literally taken this contrast times this contrast. That gives me a 4th contrast. And then this contrast times this contrast, that gives me a 5th contrast. And hey, look, we have 5 contrasts. 5 contrasts are required to fully represent a 6-group design. So one way of understanding this special case where I'm looking at interactions between one categorical variable and another is that I'm creating a set of contrasts, G-1 contrast for G's the number of groups. That's what I'm doing. So just to recap, I hope you've seen in this class and in the previous class that the same principles apply when we're looking at these kinds of designs as when we're looking at other additive and interactive designs, and when we're looking at POCs or dummy codes. They're just different reconstructions of the means. We've also learned that you can think about these interactive designs where all your variables are categorical as reconstructions of tables and of means. So that's new. The way you get there is you just literally do the data products of the their contrasts. That's what an interaction is. And that gives you a set of contrasts, which is another way of understanding what that interaction is. In this case, it's basically a set of contrasts that will represent subsets. See you all on Wednesday. We'll talk about multiple comparisons on Wednesday.